Hi everybody, my name is Masia and I'm going to be your teacher for this lab training session. My email is the one that you can see on the screen. So please feel free to send me any question or doubt that you might have about today's lab session. In today's lab training, you were supposed to generate and measure a membrane potential. However, due to the current pandemic situation, this is not possible, and we will explain you the basis of the lab session, and then we will give you experimental data from last year so that you can solve the problems and get more expertise on membrane potential. This will hopefully be enough for you to understand the basis of diffusion potential. So, you know from theory lessons that a membrane potential is created when we have two different concentrations of a charged ion across a membrane. In our case, we would have a using chamber to create the membrane potential. A using chamber is a device that has two compartments separated by a membrane, and we can add whatever concentration we want to in each compartment of the using chamber to create a membrane potential. The experimental setup for the lab session that would enable us to create and measure the membrane potential is the following. First, we have a using chamber with compartments A and B, separated by a membrane, as you can see. There is an electrode in compartment A and an electrode in compartment B, which are connected to a device that amplifies the signal by 50 times. The membrane potential created is so small that we need this device to amplify the signal. And this device is connected to a voltmeter, which gives us a readout of the membrane potential generated across compartments A and B, amplified by 50 times. Under normal conditions, you would be separated into groups and you would use either sodium hydroxide or hydrochloric acid to generate and measure the membrane potential. Now, I'm going to explain you how you would proceed to do the measurements. I'm going to use sodium hydroxide as an example, but it would be the same thing for hydrochloric acid. First, you would fill both compartments A and B of the using chamber with the same concentration, which would be 4 millimolar, of sodium hydroxide, and you would measure the membrane potential created across the membrane by these two solutions. You know it should be very close to zero, as we would be using the same concentrations for both compartments A and B. So the value that you would get in this measurement would be your offset, which you would have to remove from the subsequent measurements in order to normalize your data. After measuring the offset, you would throw the solution in both compartments A and B to the sink, and you would proceed to take the second measurement. For this, you would need to keep the solution of 4 millimolar sodium hydroxide in compartment A constant, while you would increase the concentration of sodium hydroxide in compartment B. In the second measurement, you would use 16 millimolar for compartment B and 4 millimolar for compartment A, and you would measure the membrane potential generated across the membrane by these two solutions, and finally you would write it down. To do the following measurements, you would need to increase the concentration of sodium hydroxide in compartment B by 32 millimolar, then 64 millimolar, 128 millimolar, 256 millimolar, and finally 512 millimolar, while you would keep the concentration of sodium hydroxide in compartment A constant and 4 millimolar. We will provide you with last year's measurements for both sodium hydroxide and hydrochloric acid. Take into account that the measurements we are providing you with are the raw readouts from the voltmeter, and these have been amplified by 50 times. Answer to the questions that are in the analysis part of the lab session instructions. As you have data for both hydrochloric acid and sodium hydroxide, you will have to represent a graph for each compound. This will help you understand the sign of the membrane potential created and the permeability for each ion. After you have graphed the membrane potential as it is required for the question number 1, comparing the resulting curve of the graph with the one you typically get from the Nernst equation and the Goldman equation will help you understand the permeability of the membrane for each ion. Finally, to help you set a reference system, the Nernst equation has been adapted as you can see on the screen, given the way in which the voltmeter displays the membrane potential. Note that the concentration in compartment A is part of the numerator, whereas the concentration in compartment B is part of the denominator of the quotient in the Nernst equation. Those who have to send a report for this lab session, please answer all the questions from the analysis section of the lab session instructions and also the context question. I hope all of you understood the lab session, and if you need any help, as I said, you can send me an email with all your questions or doubts. Good luck and bye!